Okay, so the last talk for today, and following this, we'll have a reception. I believe the reception is, it's either going to be right behind us or right outside. One of the two, I don't remember which. So we have the last talk is by Binghui Peng on memory regret, trade-off for online learning. Just a quick reminder also, when people ask questions, I'll hand you a mic just so that the recording picks it up for.
Thanks everyone for coming to the talk. It's my great pleasure to present our work on memory and regret trade-off for online learning. I'm Binghui, and this is a joint work with Aviad Rubinstein. So we're concerning the problem of learning with expert advice, which is a fundamental problem in the area of online decision making. In this problem, there's an algorithm that need to repeatedly make decisions over a sequence of t days. And at each day, they need to follow the advice of one of the experts. In particular, at day t, the algorithm needs to pick an expert, it, pick one of the experts. And then there's a nature that reviews the laws for all of the experts, and which is an n-dimensional vector, and we scale the value between 0 and 1. The algorithm chooses the it's expert, so the loss it receives is the loss of the it's entry. And you can see this as a game played between algorithms and the nature, and it's repeatedly played for a sequence of t days. And our goal is to compete with the best expert in the hindsight, or this is also called regret minimization, where the regret is defined as the loss of the expert received over the t days, and the loss of the best expert, where the best expert is the expert that has the smallest loss over t days. And so the goal is to obtain like sublinear regret. That is, we want the regret to scale like sublinearly in the number of days. So, or in other words, in the long term, we want the regret received at each day is of little or 1. Okay. So I missed one part when defining the problem. That's what's the power of the nature. So in general, there are two possible choices on this nature. One is we call this oblivious theory. For oblivious theory, we assume the nature knows the code of the algorithms, but it does not know the randomness used by the algorithms. And it cannot choose the law sequence adaptively based on the algorithm's past decision. Or in other words, the nature chooses the law sequence in advance. Okay. And also, we can also consider adaptive theory, where the nature chooses the loss vector, this LT, adaptively, based on the history decision of the algorithm. In particular, at day t, the loss can be chosen based on the decision of the first t minus 1 days. So the most classical and most famous algorithms for this problem is so-called the multiply weight update. In this algorithms, it means the algorithm maintains a distribution over an expert at each day. And the S expert is sampled with probability that's proportional to the exponential of the cumulative loss. Okay. This inner term is just the cumulative loss for the first t minus 1 days, and the expert just sampled proportional to the exponential of this value. So this multiply weight algorithms obtain a regret of sqrt t times log n against an adaptive theory, and this regret bound is known to be optimal. Okay. This multiply weight update has lots of applications, and it's mostly famous for being like a meta approach for designing algorithms. Some applications including like learning and games, optimization, and some algorithm problem like flows and matching. And so for these applications, you can see the excellent survey by Aurora, Hazan, and Kale on these algorithms. There's some more like broader designing framework for online learning and for regret minimization, and people usually call this like a leader selection framework. Let me also slightly talk about it. So again, the algorithm choose from some samples from some distributions, and the distribution is computed as the minimizer that minimize the cumulative loss plus some regularization term. Okay, and so this phi p is some regularization term, and if you choose, for example, if you choose it to be an entropy function, then this is exactly the multiply weight update. On the other hand, there's also another like famous algorithm called the follow the perturb leader, where the idea is just to choose the regulator to be some random noise. So here, if you plug in this random noise, then the algorithm is essentially saying, choose the best expert that has the smallest cumulative loss plus some noise. Okay, that's it. And this follow the perturb leader also obtain the optimal regret. So actually, there's a lot of different algorithms obtaining the optimal regret. But in this talk and in our work, we will take the space into the consideration, and we consider the problem of that whether we can minimize the regret using sublinear space. Okay, or equality, like how can we make decisions and choose experts without remembering their past performance. Okay, so first, a simple observation is mathematical weight requires at least omega n bits because I need to track the loss of each different expert, and in order to maintain the distribution, it already takes your n bits. Second, this space requirement of mathematical weight is comes as no surprise because it's one special case of this leader selection framework. And in general, if you just plug in this framework, you will need at least omega n bits. Because identify a leader, identify an expert that has the smallest history loss requires your omega n bits of memory. And I will and this is obtained just by a simple reduction from the communication problem of site disjointness. And just let me show you the reduction. Okay, first in the site disjointness, there's a two-party. Alice receive an n-dimensional binary vector. Bob receive another n-dimensional binary vector, and I'll view it as a indicator function. And the task of site disjointness is to determine whether XA and XB has intersection or it does not have intersection. This takes your omega n bits of communication. Now, now I will show you that any algorithm that uses sublinear space fails to distinguish the following two cases. In the first case, there's an expert that has zero loss, okay, no loss. In the second case, all experts have loss at least T over 2. There's a large gap between these cases, two cases, but you just need omega n bits of memory. The idea is for the first T over 2 days, the loss is 1 minus XA. For the second T over 2 days, the loss is 1 minus XB. You can verify if XA and XB has no intersection, then the loss is at least T over 2 for all experts. Where on the other hand, if there exists some intersection, then this intersecting coordinate just corresponds to an expert has loss 0. So with sublinear space, you should now be able to figure out which is the expert that's obtained the smallest loss, and you cannot even do it approximately. So you need to do something like bypass this leader selection framework. And let me look at this problem again, and I'll tell you why I get interested into this problem. The goal is to minimize the regret, which is defined as the loss of the algorithms minus the loss of the best expert. For any algorithm that uses polylog space, you should be able to measure. It should be able to measure its own loss, right? But on the other hand, I just showed you in the previous slide that the loss of the best expert, any sublinear space algorithm cannot track it. So you shouldn't know the second term. But then it comes a problem, right? How could you minimize the regret without even knowing the regret? In particular, if finally I define a sublinear space algorithm, I should be able to obtain very small regret. But at the end, the algorithm shouldn't have any idea of how much regret it obtains. Okay.
I was just trying to parse from the last slide. So given the algorithm, is the communication protocol that you communicate the index of the leader at every time or something like this? Okay, in the last slide, I show you that if an algorithm has sublinear space, it cannot just find the intersecting index. Sorry, I was just confused about where is the reduction to communication. So given a protocol.
Okay,
yeah,
good. Let me go back to the last slide. Okay, suppose I have a too good to be true algorithms. Then at the T over 2 days, the algorithm pass a memory state, right? The algorithm pass a memory state to t over 2 plus 1 days. And using this, using this memory state, it gives you a communication protocol.
Okay.
Okay.
Yes.
I'll just continue. Okay. Now let me spend just a few minutes, give an overview on the literature of this problem. This problem is first initiated by a work of Serenes, Woodruff, Xu, and Zhou. And in particular, in their paper, they give a lower bound, showing that any algorithms either to use at least S bits of memory, or the regret is that at least square root NT over S. And this lower bound holds even against stochastic loss. That is, the loss sequence is not chosen adversarially, but it's drawn from some distribution. So from this lower bound, you can say, first, if you have some memory constraints, then you cannot obtain the optimal regret as multiplicative weight, right? There should be some small polynomial overhead. But on the other hand, if this sequence T is very large, then this lower bound is not so much different from multiplicative weight, only an overhead of square root N over S. Okay. In their paper, they also give a sublinear regret algorithm, but they need to assume the loss of the best expert itself is sublinear. And their algorithm is for oblivious adversary. So the first sublinear space algorithm is given in my previous paper with Fred Zhang, and Fred is a Berkeley student here. We give the first sublinear space algorithm that's against oblivious adversary. So in particular, our algorithm obtains n to the delta space, and at the same time, the regret is n squared times t to the 2 or 2 plus delta. So plugging, for example, delta equal to 1/2, we provide an algorithm that uses square root n space, and the regret is n squared times t to the 4/5. So if t is very large, this is indeed sublinear. Okay. The algorithm is later improved, and by Aman Chen, and Sibyl. And they improved the algorithm and such that the algorithm uses n to the delta space, and the regret is n squared times t to the 1 over 1 plus delta. Again, if you have square root n space, this means you can obtain n squares times the t to the 2/3 regret. Again, this holds for oblivious adversary, and there's still some gap between the lower and upper bound, because you can say for both algorithms, if you only have polylog space, the regret is almost linear, right? And also in a recent work by Woodruff, Zhang, and Zhou, they also show that randomization is essential, and deterministic algorithm need to use at least omega bits of space. And they also give a sublinear regret algorithms for adaptive adversary, but again, they need to assume the loss of the best expert itself is sublinear. Okay. So in our work, we give we try to just fully characterize the trade-off between memory and regret, and actually we found out that this role of memory is quite versatile. Okay. So first, for an oblivious adversary, we just provide optimal algorithms. We give an online learning algorithm that uses S bits of memory and obtains square root NT over S regret when facing an oblivious adversary. And here in this talk, when I write this big O notation, I will omit some polylog factors. So this algorithm matches the lower bound of previous work, and is optimal up to polylog factor. From this lower bound, you can say if you are facing an oblivious adversary, then memory does not play a very critical role here, because even using polylog space, the regret is just square root NT, only a square root n overhead than the multiplicative weight. Okay. Well, for adaptive adversary, the role of memory is just changed suddenly. We prove a lower bound showing that an online learning algorithm requires at least square root n over epsilon bits of memory, or it needs to suffer at least epsilon square t regret against the adaptive adversary. Let's parse the result. First, it says if you want to obtain t to the 0.99 regret, then you need linear space. Okay, especially given if t is super large, then you need square root n space. Second, if you just want to obtain a slightly sublinear regret, and the regret is little all of t, then you need at least omega n bits of memory. Okay. We also give a near matching algorithms. We show that there's an algorithm that uses square root n over epsilon bits of memory and has regret epsilon t. So in the previous slide, the memory is the same, but the regret, the lower bound is epsilon square t. Okay. But adaptive, sorry. question?
I think I'm having trouble parsing it. So you said if you want sublinear regret, shouldn't epsilon then depend on t and not
no,
n?
No. If you have here epsilon is belong to like 1 over square root n and 1. Okay, some number between 1 over square root n and 1.
But shouldn't there be some relation between that and t? I mean, sublinear usually means
sublinear
less than t. Sublinear in n.
Yeah.
Okay.
Because multiple weight itself just use n space, so it does not make sense if you have x smaller. So this just shows like a square root n memory. It's both necessary and sufficient to obtain sublinear regret. Okay. Any questions so far? Cool. I will try to give an outline of how we obtain this result, and I'll reverse order. Start from the algorithms for adaptive adversary, which is the simple and I think probably more conceptually interesting one. Let me first give you some overview on this result. So first, let me just I'll just sketch high level the challenges here. I already argued that sublinear space algorithms, you cannot hope to identify the best expert or just even estimate its loss approximately. For adaptive adversary, there's a second challenge. So for example, even if we are just very lucky and we just happen to figure out what's the best expert, right? We figure out this best expert, we just keep playing it. It still does not work because the adversary is adaptive. It can assign a very large loss once you keep playing this best expert. Okay. And the high-level idea, I will give a more concrete algorithm description, but the high-level idea is actually twofold. So first, we don't really need to compete with the best expert. We only need to compete with some expert has relatively good performance. I'll define what's a good expert later. And also the second idea is once you find a good expert, you should keep it long. So even though the adversary could immediately assign very large loss to it, you should still keep it very long. This is slightly bit like counterintuitive, but I'll explain it. So in our algorithms, the algorithm relies on two subroutines. So each subroutine itself does not give you any like sublinear regret, but when you combine them, you will obtain the final algorithms. So first recall, we want to obtain epsilon t regret, and we partition in algorithm we partition this sequence of days into epochs of size 1 over epsilon squared. Okay, algorithm 1 is quite simple. For each epoch, you just randomly sample certain experts, and you run multiply weight over them. Okay. What's the intuition here? Intuition here is by running algorithm 1, it should be competitive with the square root n's best expert, right? Even though it does not have any guarantee on the best expert, it should be good enough to compete with the square root n's expert, and but at the same time, it has no guarantee when comparing with the top square root n experts. For algorithm 2, it's a bit complicated. Again, for each epoch, it runs multiple weight. But this time, this runs multiple weight over a subset of experts, and the subset is not obtained by random sampling, but I'll explain how we maintain this subset. At the beginning of each epoch, algorithm 2 would sample square root n expert. It just keep it in the memory and secretly observe their loss. And at the end of this epoch, the algorithm just choose the best expert and add it to this subset P and keep it for square root n over epsilon epochs. Okay, I'll go over this again, but so our final algorithm is just, again, running multiple weight over these algorithms. So what's the intuition of the second algorithms? Remember, the bad case is, the best expert in the hindsight, this I star, it's among the top square root n expert. In that case, with probability 1 over square root n, algorithm 2 would sample I star. And with high probability, if I star is sampled, then it would be the best expert in the sample set, and it will be kept for square root n over epsilon epochs. So summary, with probability 1 over square root n, you don't need to worry about this, the competing with the best expert for square root n over epsilon epochs. Let me show you how to analyze the regret, but let me first try to repeat the algorithm again. We divide the sequence into epochs of size 1 over epsilon square. Okay? For the first algorithms, it's random sample a subset, run multiple weight, and then random sample a new subset, run multiple weight. You keep doing this. For the second algorithms, it random sample a subset, but it just secretly observe the loss of this expert in the subset. Okay? And at the end, you just keep the expert that has the best performance, and you keep it for skeleton over epsilon epochs. You continue in the second epochs. You sample a subset and you observe the loss, and you keep the best expert for like skeleton over epsilon epochs. Now let's do the analysis for the regret. So we go over the epoch one by one. For each epoch, we ask a question: is it among the top skeleton expert inside this interval, inside this epoch? If no, then we know that algorithm 1 should be competitive with it, right? So I'll say it's a blue epoch, and we don't need to worry about it because algorithm 1 is competitive with it. Well, for the second epoch, we can keep asking the question, and if the answer becomes yes, that is the best expert, it's actually among the top skeleton expert inside the epochs. Then, unfortunately, algorithm 1 is not good enough, and we need to suffer large regret in these epochs. But now, let's look at algorithm 2 and ask the question whether this I star is being sampled. If so, by the definition of the algorithm, it would be kept for square root n over epsilon epochs. Then we will assign the next square root n over epsilon epochs as a yellow epoch. So in general, there's 3 types of epochs at the end. For blue epochs, the regret is at most epsilon because of algorithm 1. For yellow epochs, the regret again is epsilon on average. Because this yellow epochs, the expert keeps it in algorithm 2's memory and it runs multiple weight. For red epochs, we don't have any guarantees. The regret is 1. But I want to say the length of yellow epochs versus the length of red epochs is 1 over epsilon. The reason is with probability 1 over for each red epoch, with probability 1 over square root n, it will be sampled and kept for epsilon over square root n over epsilon epochs. So the ratio between yellow and red epoch is 1 over epsilon. So at the end, you don't need to care about this red epoch. It brings you like a epsilon regret in total. Now let's analyze the memory. Okay. So for algorithm 2, it's quite obvious. It stores square root n over epsilon expert in total. So the memory is square root n over epsilon. For algorithm 2, actually, I claim it needs to store square root n over epsilon square expert in its memory. You may wonder why not square root n, right? We only want to compete with the with the square root n expert. Okay. If you are facing an oblivious adversary, then sampling square root n expert is enough because the algorithm cannot look at your memory state. So at the beginning, you sample square root n experts with high probability. It should catch the top square root n expert. But for adaptive adversary, this is not the case. So consider the following simple example. All the experts have lost 1, but only square root n of them has lost 0. In this case, if you sample square root n expert, you will only sample 1 of this square root n good expert. Right? Expert has lost 0. But once you when you run the algorithm, once you commit this expert, the adaptive adversary can immediately assign high loss, large loss, like loss 1 to it. So sampling square root n expert is not enough. But indeed, there's a common trick that transfer an algorithm that works for oblivious adversary to adaptive adversary, but with some blow up computation resources like memory or computation and so on. The idea is we sample square root n over epsilon square expert, and we just divide it into 1 over epsilon squared group. So each group contains square root n expert, and we just run multiple weights separate for each group. At the top state, the decision follows from the top group. Let's say at each day, I just look at the decision of a new group of experts and follow it. This means the algorithm itself is, does not depend. The decision does not depend on history. So the nature also does not need to be adaptive. There's no benefit to be adaptive. Okay. So I just give a short explanation on why the memory here is square root over epsilon squared. So in summary, the memory of the algorithm I described is square root over epsilon squared, and the regret is epsilon t. And so it's have some slightly overhead than the one I claimed. So it turns out you need some extra work, but I won't talk about it. Okay. Now I will show the lower bound and show why your square root memory is necessary in order to obtain sublinear regret. Question?
I have a question on the algorithm. When do you choose to play? Thanks. So for the algorithm, when do you choose to play experts from algorithm 2?
Okay. So the final algorithm is runs semantic weight over algorithm 1 and algorithm 2. Okay. So
yeah, over what time period?
For restart from every 1 over epsilon squared days.
Cool.
Yeah. Cool. Let me continue with the lower bound. Okay. I will show you in this talk why square root n memory is indeed necessary if you want to obtain sublinear regret. Okay. So in order to construct a adversary, you need to obtain the following two goals, right? So first, the loss of the memory bounded algorithm is large. Second, the loss of the best expert is small. Right? That's kind of true goals. So the intuition is follow. If an algorithm has memory S bits, then intuitively it can only remember as good expert, right? Again, I won't give a formal definition of good expert, but intuitively it only remember as expert. But the problem is, how could we attack this algorithm? How could we make this as good expert inside of the algorithm's memory, and how do we make them bad? Nature does not know exactly what is as good expert, but what it can do is that it can attack the most as recently played expert. We want to attack the expert inside the algorithm's memory, but instead the nature just attacks this as most recently played expert. And attack means assign large loss to them. We also need to make sure the loss of the best expert itself is small, right? So so here, they are as good expert, but probably the nature could assign large loss to them. The idea is you have maintained 10 as good expert. And so it's fine, as of them have large loss, and eventually one of them should be good. Okay, I will give more in detail, but that's some very high-level intuition. So I want to give an intuitive explanation why square root n memory is necessary. The idea is follow. So every round, the nature can only attack one expert or assign large loss to one expert. And we want to make the rate of obtaining one good expert is slower than the rate it's been attacked. Okay, what's the rate of obtaining a good expert? The algorithms can store S bits of informations, and intuitively it could look at S entries, S expert in each round, and what's the probability of each expert being good? 10s over n, right? There are 10s good expert, and so if you multiply these two terms and set it equal to 1, this means the bottleneck here S should roughly be square root n. Okay, I will show you how we derive this result formally. So I'll first introduce the problem multi-set disjointness, which is just multiple independent copy of this the basic problem set disjointness. Recall, in the set disjointness, there are two parties. First party receive a binary vector, and the second party receive another binary vector, and they want to. And here I consider a search problem. So they want to figure out the index that's intersecting. And the goal is to output this intersection. The multi-set disjoint is just a multiple independent copy of this basic problem. So we make capital K copies and of the basic problem, and the final output is to output the index set. So for each copy, there's a one index intersecting coordinate, and if we make k copy, then it's the size should be k. Okay. Now let me describe the hard sequence. So we partition the expert in capital K groups, and each group have capital N expert. So we take capital K and capital N to be sqrt N. And here, I'll just define the good expert to be those like in the intersecting set, and it will be clear soon. Again, I will partition the entire sequence into epochs of size sqrt N over 4. And the nature will just assign the loss for each epoch just completely independently, so I only need to describe what's the loss for each epoch. What's the loss for each epoch? So there are sqrt N over 4 days in each epoch, and at the t states, with probability 1/2, the loss is 1 minus xa. With probability 1/2, the loss is 1 minus xb. Okay. But at this point, the nature is not adaptive, right? It's completely ignorant of the algorithm decision. Oh, sorry. The adaptivity comes from the last sentence. There are some exceptions for this rule. The exception happens for those experts that has been played in the first t-1 days of these epochs. For those experts that has been played, the loss is high, it's 1. Okay. Now look at this sequence again. For those good epochs, that's so for those good experts, that's the expert inside this index set I. Its loss is always 0, except it has been played sometime at the same epoch. Well, for those experts that not belong to the capital I, the loss is at at least 1/2 in expectation. So okay. Let me show you the analysis, but let's first just make a simple claim. So I claim there exists one good expert, I star, inside of this index set has lost at most 1/4. The reason is that if there's no exceptions, then every expert in I has lost 0. Okay. But now inside each epoch, probably there are sqrt N over 4 experts will have lost 1. Then probably sqrt N 1/4 fraction of expert in the index set receive loss 1. But it's fine, right? The total size is sqrt N, and only 1/4 of them has lost 1. On average, there exists one expert that has lost at most 1/4. Okay. Now I show you that the best expert in the sequence has lost at most 1/4. Let's prove by contradiction. And let's assume there's an algorithm that can obtain like a sublinear regret. That's to say, its loss is roughly sqrt N. It's roughly 1/4. Okay. And I claim the algorithm needs to play at least sqrt N different experts of I in each epoch, and that's on average. The reason is as follows. So for experts that's not in the index set I, its loss is roughly 1/2, right? So you cannot always place it. So you should spend a significant amount of days to play expert inside of the index set I. But also for each epoch, it does not make sense to play an expert twice, because the second time you place it, the loss becomes 1. Okay. Combining these two facts, you can show that the algorithm need to commit roughly like omega sqrt N experts in each epoch. Let me show you the reduction. Okay. The nature divides the sequence into epochs. Let's just zoom in an arbitrary epoch. At the beginning of this epoch, the algorithm transfers the memory state as 0. Right? As 0 is the memory state at the beginning of the third epoch. The algorithm first need to play an expert. Let's call it I1. And then it observe the loss. The loss is with probably 1/2 is 1 minus xa, and with probably 1/2 is like 1 minus xb. But let's just assume for now it's 1 minus xa. Then it updates the memory state. Again, commit an expert, observe the loss, and so on. Repeat it for sqrt N over 4 days. Okay. So what's the total message passing here? There are squared n over 4 rounds, and each round, the total number of bits is s bits, right? S is the memory state. So the total memory passing is squared over 4 times s. But there's some exception. Because at the beginning, the memory state, you also need to take account into the memory state at the beginning, right? And this initial state is quite different from this the message passing inside epoch, because it's and also it's not some some random bits, because intuitively in later epochs the algorithm itself observes this loss sequence xa and xb for many times. So this initial state should contain a lot of information. But fortunately for memory bounded algorithm, it's not too large. And then finally, the guarantee is that this expert 1 to xy1, i2, i3 played in this epoch should have a large intersection with the index set. The intersection is omega n. So what's the correct communication? Actually, it's not exactly multi-site disjointness, but instead I'll call it a multi-site disjointness with advice. And this advice capture this initial state. Now this becomes a three-party communication problem. Alice, Bob, and Charlie. Charlie here observes both xa and xb. Okay? And the communication as follows. Charlie first sends s bits to Alice and Bob. And Charlie's role is just the initial memory. Okay? And after that, there's just a two-party communication. Alice and Bob perform multi-round communication. And at the end, they output an index set that have a large intersection with the target index set I. Okay? And I will prove a lower bound for this communication problem. The lower bound says either s is greater than omega k. That is the first round message sent by Charlie is greater than omega k. Or the transcript in the second stage, like the transcript between Alice and Bob, is at least K times capital N. So this bound is sharp. The reason is, for example, if Charlie can send k bits to Alice and Bob, then Charlie can just send this intersecting index to Alice and Bob, right? So problem then becomes trivial. And also, if the transcript pi has k times n bits, then Alice can just send xa to Bob. Again, the problem just becomes trivial. And I'll show you actually one of them need to be held. But now let's recall what's the parameter setting in our problem. Capital N, capital K, both is set to be square root n. And the transcript, as I argued in the previous slides, has square root n over s bits. So by proving the lower bound, I should be able to prove the memory s, this s should be at least square root n. Okay, so all I need to do is to prove a lower bound for this multi-site disjointness, this advice. It turns out that I will go back again to multi-site disjointness, and I will use a very strong theorem by previous work. Let's call it direct product theorem. But let's go back to multi-site disjointness. And again, I want to the goal is to output a set that has large intersection with capital I. But here I only require the output has large intersection with non-trivial success probability. That success probability is at least 2 to the 0.01k. Okay. So if you allow the success probability to be 2 to the minus k, then the problem is trivial, right? So Alice and Bob can just randomly output some coordinates, and the success probability is just exponentially small. But here I want something slightly non-trivial, and I want the success probability to be slightly larger than this 2 to the minus k. And it turns out that that's a very powerful and amazing result by Rubinstein and Rubinstein, where they show that if a communication problem has information complexity capital N, then any protocol trying to solve k independent copy of f needs at least k times capital N bits of communication, or the success probability is exponentially small. Okay. Set disjointness have information complexity capital N, so just plugging this. Let's prove a lower bound for this multi-site disjointness, and it turns prove a lower bound with multi-site disjointness with advice. Any questions so far? Okay, I will go to the final part, and unfortunately, Yeah.
So here, this is a case when there is no prophet or like there is no Merlin that can correlate XA and XB, yes?
Yes.
What do you get for that case?
Oh, sorry. So XA and XB come from the distribution of set disjoint. So set disjoint itself has some correlation. So it's not product distribution. But
No, sorry, that's true. But still, you don't have Charlie here.
yeah, I don't have Charlie now.
Okay.
The reason you can eliminate Charlie is Charlie provides a useful advice of S bits, right? But here, Alice and Bob can just randomly guess this S bit. And the success probability is 2 to the minus x, S, right? And so essentially, we remove Charlie and put Charlie into this success probability.
Good. So then this works for any other problem that has large information complexity.
Yes. And this result by Bruman and Rubinstein for any two-party communication problem with large information complexity.
Okay, thanks.
Okay, I'll just continue and go to the final part and talk about the oblivious theory. And unfortunately, the algorithm is complicated. So I'll try to give a very good high-level idea of these algorithms. Okay, and I'll try to omit many details. So I'll only focus on algorithm that use polylog space, and I'll try to obtain a regret of sqrt n over a regret of sqrt n times t. Okay, and it's fairly straightforward to obtain the general trade-off. Again, I partition a sequence into epochs, but here I use capital B to denote the epoch size. And similar as previous algorithms, the algorithm still runs multiple weight over a carefully chosen subset. And it runs multiple weight over the subset at each epoch and restart afterwards. The cool thing is this algorithm is always competitive with the best expert inside this subset. This has come from the regret guarantee of multiple weight. And so this remains to prove that the best expert in this carefully chosen subset is comparable with the best expert in the hindsight. Okay, and you can see essentially I describe all the details of the algorithms, except I omit the key part. That's how we choose this subset P. How should we choose this subset? So in the algorithm, I will update the subset at the end of each epoch. Okay, let's update every epoch. So we need to add some new expert. So here in Qt, you have no information outside the subset. So probably the best you can do is just random sample a new expert into subset. But you cannot keep adding expert. You also need to remove some expert. And the problem is very easy if all these experts joining in the subset at the same time. For example, if they are all joining in the second epoch and at the end of the fourth epoch, what you can do is you just keep the best expert, right? But the challenge is that these experts joining in the subset at different times. Some of them are sampled in the first epoch, some of them sampled in the third epoch, and so on. Now it's really hard to argue which expert is good, right? Probably some expert has a large loss, but it stays for longer. So it's quite it's not exactly clear how to choose this. But our key idea is the benchmark is chosen to be the algorithm itself. So key conceptual idea here. We would remove expert that performs no better than the algorithm itself. Intuition here, if an expert I stays in the subset, stay for long, but remove it does not hurt the performance of the algorithm. Or remove expert I, the algorithm is still better than the expert I. So then expert I is not useful, right? This is a sketching workshop, so I just give a name of this algorithm as expert sketch. Okay. The key definition is the meta expert. For a subset P, I define a meta expert that chooses the best expert for each epoch and play this best expert. That's to say, for each epoch, the meta expert look at the expert in subset P and choose the best one and play that for the entire epoch. So it really makes switch its decision like over expert in P. Now, for each expert in the subset, if expert I is not strictly better than the meta expert defined over P minus I, then I would remove expert I. And here, strictly better is the strict definition is that the performance of expert I is not smaller than the meta expert minus 1. Okay, that's the formal definition. And intuitively, this means if expert I is not strictly better than the meta expert, then it means it could be replaced by the combination of other experts. Okay, that's the intuition. And I'll give you some demonstration. So let's imagine at the end of some epochs, there are 4 experts of the subset, and I want to run the expert sketch and remove some of them. And let's say this is loss for each interval. Okay. I'll show you how to run these algorithms. So first, I'll just start from expert 1. And the meta expert is chosen to be the epoch best expert of 2, 3, and 4. Then the best one is just 3. Okay, the minimum loss is 3. So in this case, expert 1 is much better than this meta expert, so I will keep expert 1. Now consider expert 2. I will take a epoch-wise minimum over the last and the second last segment, and the minimum is 1 and 4. But now this time the total loss over this 2 interval is 5. It's smaller than expert 2, right? Then in this case, I will just remove expert 2, and I'll continue and consider expert 3, and now the algorithms run, and the meta expert is defined over expert 1 and expert 4, and you can see the pair-wise epoch-wise minima is 1, 4, and 8, and the total loss is 12. It's equal to expert 3. In this case, expert 3 is not strictly better than the meta expert, so just remove it. Okay. Now, the immediate benefit of this algorithm is the memory analysis become quite easy. I claim the number of experts is never more than log t. Why is that? Let's assume these are the experts that survives after this expert sketch algorithms. And then let's assume the loss of the last expert is x. Then I claim the loss of other expert on the last segment should be at least x plus 1. Okay? This can be just follow some definition, because if some of them has loss at most x plus 0.5, then the meta expert has loss also at most x plus 0.5. And so it's not, so this last expert is not strictly better than meta expert, so it should be just follow the definition. If you repeat this analysis, you can actually find, if you move to the second last segment, you can find the loss of this expert actually, the gap become large. Actually, if the loss of the second last expert is is y, then the loss of other experts should be at least y plus 2. Continue, this gap become larger and larger, and so summary, for the first segment of the S expert has a total advantage of 2 to the I minus 1. That is to say, the loss is its loss is at least 2 to I minus 1 smaller than other expert. Of course, the loss could be at most t, right? So this means the number of experts is never more than log t. And if you look at the algorithm carefully, the algorithm actually doesn't need to remember the loss of each epoch. Instead, it only need to remember the loss of each expert of each interval. So the final memory actually just scales quadratically with the number of experts. So there are at most log t experts, so the memory is log t squared. Okay. Now let's bound the regret, and let's fix all the randomness at the beginning. The randomness of the nature, the randomness of the algorithm, so the loss sequence is fixed, the excursion of the algorithm also fixed. Okay. And I'll do some intervention. Okay. Consider the hypothetical situation that we add the best expert I star to the subset at the beginning of epoch t, and we start from the first epoch. We just manually add best expert to the subset and see what happens. There are two possibilities. One, the best expert survive till the end. Second probability, expert I will be removed by this expert sketch at some future epoch, let's say T prime. In the first case, the I star will survive. I'll just move to the next epoch, and I'll say this epoch is a bad epoch. Okay. And for the second case, I star will be removed at some future point. I'll then just call this the epochs between T and T prime, call them good epochs. And I'll start from T prime plus 1. This is the epoch after it's been removed. This is the definition for bad and good epochs. And let me show you some demonstration. So we fixed the randomness, so the excursion of the algorithm is completely fixed. This subset is also fixed. Okay. Let's do some intervention and add the best expert to the beginning. Suppose it survived till the end. Then according to the definition, the first epoch is a bad one. And then we move to the second epoch and we add it to the subset. But now suppose it will be removed at the end of the third epoch, removed by the expert sketch. Then I'll call these two epochs good epochs. I'll keep doing this. In this example, the next epoch is still bad epoch, so I'll just do. Now let's do the regret analysis. For good epochs, I claim the regret is trivially controlled. Intuition. The definition of expert I guarantees that, okay, if I star is being removed at the end of this good epochs, by the definition of expert sketch, it means I star is replaceable by our algorithm, right? So the performance of our algorithm should be not worse than I star. So for good epochs, the regret is essentially 0, or essentially like some trivial one. For bad epochs, unfortunately, we don't have any control over the regret. But recall how we define a bad epoch. The definition is that if we do some intervention and we just manually add I star at the beginning of that epoch, it will survive till the end. But what's the probability of sampling I star and add it to the subset? Right? It's 1 over n. So hopefully it should be at most, there should be at most n bad epoch, because once you catch the chance and you really add I star to the subset, they will survive till the end. But unfortunately, this analysis turned out to be circular. The rough reason is we already fixed the randomness at the very beginning. So we consider a situation that we sampled, that we do some intervention and add I star to it. But if in the execution of the algorithms you really add I star, then it might kick off some other expert. But then say I1 and then some other expert I2 might just be kept because I1 is removed, and then I star will actually be removed sometimes in the future. So short summary is that we fixed randomness at the beginning, so we can't really do the analysis. So it turns out the final algorithms become complicated than this one. So we need to change the algorithms and also change the analysis for memory. Okay. But fortunately, the regret is similar as analysis in the. Okay, good. One minute. Regret is similar. So let me just quickly show you the analysis. Okay, first there are 3 terms for the regret. The first term comes from multiple weight. There are T over B epoch, and each epoch the regret is scored at B. Second, for each bad epoch, we don't have any guarantee the regret is B, but if the analysis goes through, the number of bad epochs n, so it's at most n times B. For good epoch, essentially no regret. Okay, if you balance the term, then the regret becomes T to the 2/3 times n to the 1/3. This is this is still it's already has some improvement over previous work, but there's still some gap between our final bound. But the improvement idea is quite simple. So for bad epoch, we say we suffer B regret. But the idea is you can restart your algorithms. You can maintain a separate thread of your algorithm and restart every B days. So for those bad epochs, you shouldn't suffer B regret. But the regret should be at most B to the 2/3 times n to the 1/3, because we already have a good algorithms. You keep repeating it, and you get a regret bound of sqrt T times n. Again, there's some gap, and we actually need some actual work to get optimal regret. Okay, this is just a table that summarizes the result of this paper, and I reparameterize it a little bit. And the gap, the technical question here is, close the gap for adaptive adversary. There's still some like a small polynomial gap here. Yeah, so let me just summarize future directions. So for example, memory graph trade-off for other problem. Also, I like this algorithm of multiple weight because there's many applications. So it's interesting to see if it's possible to use our algorithm, our idea to attain some like other bounded memory algorithm. And finally, I also think this our lower bound strategy for adaptive theory might be useful for other like problems. I think especially this direct product schema for Brimmer and Rubinstein S-theory is quite powerful. Okay, I'll wrap up the talk here, and thanks everyone.
Any questions for Binghui?
So I guess like what's the high level challenge in trying to get low memory versions of all these different applications?
Okay, very excellent question. So after I designed this algorithm with Aviad and also with Spread, we also try to think about more probably there are some very easy applications. There is some easy application. For example, for games, there's some connection between regret minimization and coarse correlated equilibrium. For that case, indeed you can just plug in our result and give some bounded memory algorithms. But for other problem, especially for example, I consider problem of learning some graphical model, which there's also an excellent paper by Adam Kavalian as the co-authors showing how to use multi-weight to design some algorithm for learning graphical model. But it turns out the adversary model here is even stronger. Okay, so here I'm thinking about the case that every round you commit an expert, but this committed expert is not revealed to nature. Otherwise, nature just assign a large loss to it. It's just that. It turns out there's a more strong adaptive setting. That is, the algorithms each time does not commit a single expert, but commit a distribution. Okay, for multi-weight, it's does not sample from sample a single expert, but just commit the distribution to the survey. In that case, multi-weight still works, but our algorithm breaks. And indeed, we show a lower bound actually nothing can do here. You need omega n bits of memory to obtain sublinear little OT of the graph. So unfortunately, I think at least for that graphical model application, there's some gaps here, and I feel probably it's also the gap also exists in other setting, but yeah.
Any more questions for Binghui? If not, then let's thank him one last time. Okay, before people, okay, so now.